can close this.
Okay.
So thank you. Let me just try this. Okay, cool. Yay. Thank you. Yes, so just a little prelude. ICAPS 2008, which was held in Sydney, where I now live. It was the first conference I ever attended and presented at. So it's very special to me to be standing right here to present my dissertation to you right now. And I have so many people to thank for this journey. Of course, my supervisors, Adi, Phil, and UC. Adi especially has been my supervisor since my honors year, so for altogether 5 years putting up with me is a great feat. And thank you to ANU and NICTA for giving me the opportunity to study for my PhD. They are both great institutions to study at. And thank you, ICAPS community. I love you guys. And I want to thank Nathan for providing the HOG framework, which I've used heavily for all my experiments. And I've also been really lucky to have really great mentors. Sylvie, our lab director, and Malte and Sven at DC's giving me great advice. And of course, I want to thank my family for their unconditional support all my life. So, for my PhD, I looked at techniques in multi-agent pathfinding, addressing major issues to do with scalability, completeness, optimality, and I won't be able to cover all the algorithms in full details, but there are two main algorithms during the course of my PhD, and I'll illustrate how MAP works. And it's the cooler algorithm because it provides some cool properties such as completeness guarantees and have theoretical low polynomial upper bounds. And then a highlight of experimental results and finish up with some conclusions. So the pathfinding problem involves finding a sequence of moves that takes an agent or multiple agents from their start locations to their targets. And in the work of my thesis, I assume the environment is fully known and static, with static obstacles. And the units are moving in the presence of simultaneously moving units, and they have to avoid moving into the same location at the same time as would be expected in real world. And the goal is, in this cooperative setting, is to navigate every unit successfully to its target. And here is so to abstract this geometric continuous problem into a discrete environment is very useful for producing efficient algorithms. And here I show you a simple example where you can see we have the units bounded in spheres of diameter d, and the targets are the same color in squares. And would you switch to the simple example movie just to give you an idea? There's some overlap in the paths they computed, but they are able to resolve their conflicts as they move along, and they have successfully reached all their targets. Yeah, cool. And, oh, no, why is it moving? Yeah, so this getting moving entities to where they want to go. It's not just a very important task in our everyday lives, but also for mobile robots, game characters, and for applications like logistics, disaster rescue, military type of operations. And when avoiding colliding into when units when there are multiple units, you have to deal with avoiding collisions, and the state space is exponential in the number of units, so it becomes computationally much harder than a single agent case. And we have some complexity results where, for a particular case of grid-based pathfinding, the n-squared puzzle, it's NP hard to determine if a solution for at most k moves exists. And in a related multi-robot problem where units can move into a location at the same time as the previous occupant is leaving, is shown to be NP complete also. And when we consider variations to the problem like movable obstacles or different size units, the problem becomes even harder. On the other hand, the approximate algorithms can run in polynomial time. So traditionally, there are two main approaches to handle multi-agent pathfinding. And in the coupled approach, both approaches, I should say, have specific strengths, but also limitations at the same time. And in the coupled approach, where units plan globally in the global state space, it's got the desirable theoretical properties of being cost optimal and complete, but the state space also grows very quickly in the number of units. And so when we want to solve problems of significantly larger size in hundreds and even thousands of units, we have to take a different approach, which is to decouple that big global search into a series of smaller searches, and it can achieve much faster speed, scale up to much larger problems, but at the same time, you lose the optimality and completeness guarantees. So this, and that is seen in our earlier algorithm, the FAR algorithm, which is very fast and efficient, but incomplete. And in our MAP algorithm, we want to address these issues with completeness and tractability. And so MAP looks at the features of the problem and extracts information. It is designed to be able to tell if it can solve a problem, and for solvable instances, it runs in low polynomial time and provides solutions, and also with low polynomial length upper bound. And it is also designed to scale up to, which is our main interest, to solve much larger problems than before, and to cover a wide range of problems common in computer games or robotic type of applications. And we also look at a number of optimality criteria, such as make span, travel distance, and total number of actions, including weight actions. So, MAP can define very well specified conditions for problem instances it can solve. And it can determine in low polynomial time, because these three conditions are quite easy to check. And so firstly, a problem belongs to this class that MAP the basic map algorithm. I'll just start with the core algorithm for now. And the first condition is for every triple location along the path of a unit, there is an alternate path that connects the two end locations without going through the middle location, where you see that unit U is the omega path connects I plus 1, I minus 1. And we chose that symbol big omega because it is shaped like it's avoiding the middle. And also the second condition is every unit has in its first step of the path, no one is occupying that location, so an initial blank. And the third condition is that no paths cross the target of other units. So these conditions may seem restrictive, but we formally relaxed them in stages of my thesis. I unfortunately won't be able to cover all the details, but I will show you very shortly how the intuitions behind our relaxation of the alternate connectivity, the first condition. And and the previous three slidable conditions are specified so to enable this blank traveling operation, which is at the heart of the map algorithm. So when a blocked unit U, it's trying to move along its path, and it will seek a blank from somewhere along that alternate path to slide those blocking units A and B along and enable progression. So for the paths, pre-computed paths, every unit is guaranteed to reach, every slidable unit is guaranteed to reach its target along that path. And so you can imagine tunnels make the alternate connectivity condition very hard to satisfy, or impossible to satisfy, even if it's the two regions of the map are disjoint otherwise. And so the idea, since we use the alternate paths to bring a blank, we can actually generalize that idea in a more general buffer region somewhere else in the remainder of the path segment to bring the blank. Because if you see, even in this somewhat extreme example, where every unit is trying to get to its target on the other side of the bridge, and there is no alternate path for the length of the bridge. But on either side of the bank, there is still lots of blanks for the units to utilize in a more general blank traveling operation. So we have been able to extend the slidable class much greater, and whilst preserving the properties in the original map algorithm, preserving the low polynomial upper bounds. And the full details are in the thesis. But here I'll give you an example of the problems that we deal with. We use game maps from BioWare's game Baldur's Gate, and as said before, we use large maps of between 13, almost 14,000 to over 51,000 nodes. And I don't know, switch to the other video. I'll only show a snapshot of it. But so there are 1,000 units placed randomly with random targets, with a target also placed randomly somewhere on the map. And I also zoom in because otherwise they are too small to see. But I hope you get the idea that these maps are really non-trivial. It contains narrow entranceways that lots of units need to pass through. There are rooms, corridors of different sizes, shapes, and yeah, thanks. Back to the slides, please. Cool. Okay, this is the right, yeah. So here I'm showing you the, so each graph line represents the number of units solved for one of the 10 maps we used. And on the left is the success ratio of WHCA star, is one of our benchmark algorithm. And in the middle is FAR, our algorithm FAR, and map on the right. And yeah, so for the incomplete WHCA star and FAR, we set a 10-minute time limit to give it plenty of time to solve the instances. And then, so in this one, we only let map solve the solvable instances that fall under the extended slidable conditions. And if we just let it try to solve all the units, it performed even better. And now it closed that small gap, and all the 10 graph lines match very closely to the total number of units in each problem instance. And here I'm showing you a summary of the solution quality, and this ratio is obtained from the dividing the value of map over the benchmarks. And so I also, besides the benchmark algorithms, we also compare against a theoretical optimal lower bound, because we cannot, at this scale, obtain optimal values. We just use a very simple, relaxed problem where we compute the optimal solutions by ignoring other units. So it's basically a set of single agent shortest path. And I should point out that this is very clearly smaller, especially for make span and the total number of actions. And this estimate grows increasingly underestimates the true optimal value because it ignores the weight actions. Okay, maybe I'll skip some, but this was just to illustrate how a lot of maps computation can be taken into an offline preprocessing step. Maybe I won't have time for that. But our experiments showed that FAR was very, very fast and very effective in a lot of cases, even though it suffered the same limitations of decoupled approaches. And MAP is the clear winner in scalability and success ratio, and it has strengths in that it provides these theoretical upper bounds, and it is also competitive in empirical performance with the very fast but incomplete algorithms. So, yeah, it's pretty cool. And so some future work, but there's still lots of room for improvement and possible extensions for MAP. But I'll now move on to questions, and I'll leave you with a quote from Lord of the Rings that shows even an adventurous hobbit cannot plan globally where it wants to go.